Good morning, Chem 1310. I hope you guys are having a great Thursday. Today is Thursday, the 11th, September 11th, 2025. Um, and so what I am going to do is start recording. I'm also going to go ahead and share my slide deck with you guys. Um, what we were talking about on, what was that day? That was Tuesday. What we were talking about on Tuesday was atomic structure. And at the heart of our conversation of atomic structure, we were kind of looking at, well, where are electrons? That's really the question that we're seeking to answer. Where is an electron? And where are electrons? So if I show you this right here, this image on the right-hand side, that is a line spectra. And what I want you to think about with respect to this is that each one of these colors represents how an electron behaves. Okay. And whenever, like I have four boys. They're wonderful. My oldest is 8 years old, 9 years old. 9 year old as a couple of weeks ago. And one of the things that um we talk to his teachers about from time to time is, well, his teacher will say, oh, well, he didn't behave during X, Y, and Z. Like we were having, circle time or we were reading books, someone was reading and he wasn't behaving. And it's like, okay, that's not something that I want to hear. And not like, don't tell me that, but instead like, that's not good. Um, but then we kind of have a conversation with the teacher, like what inspired or what motivated, why did he behave that way? And, what was the behavior? So, what I want you to think about here is this is a hydrogen atom and the behavior of a hydrogen atom's single electron. Okay. Now, this right here reflects how the electron behaved. But the question is, well, what motivated it or what caused it to behave in that way? And when it comes to electrons, what we're talking about is the input of electrical energy. Okay, so we kind of electrocute an electron or electrocute an atom or atoms. And the electron that this hydrogen atom has, it behaves in three possible ways, or in three different ways. I don't want you to memorize these three different ways. I just want you to think about them as these three colors represent the way that the electrons of a hydrogen atom respond to this electricity. And this is kind of the display or the manifestation of it. Now, what that tells us is that tells us basically where an electron can possibly be and where it can possibly go. So we have this kind of classical model of an atom where at the center is your nucleus. And at the center of your nucleus, we've got protons and neutrons. So your nucleus consists of protons and neutrons. Then outside of that are electrons. And if you're talking about a hydrogen atom, you only have one electron. If you're talking about helium, you got two electrons. Now, this gave us the opportunity to start building what's known as electron configurations. And so this was a matter of like assembling electrons. Now I'm going to go on to the next slide because I'm going to go through three different electron configurations. And there's the way that you kind of write out an electron configuration is you first write a number. So I'm going to use an X. X being simply a number. Then you're going to write a lowercase letter. That lowercase letter can be S, P, D, or F. Those letters correspond to these different shapes where electrons can possibly be. Then after that, so I'm going to write X, S, and then I'd put an exponent number. Now that exponent is going to tell you how many electrons are in that specific subshell. Now, what I want to do is I want to show you, first of all, the electron configuration for helium. Helium has an electron configuration of 1s2. Now I want to deconstruct that. Why do we give it the number 1? The reason for that is because we're looking at the row on the periodic table, and the row that helium is in is 1. So the first 2 electrons that helium has are in the 1s subshell. Now, after that, we have, so helium's electron configuration is 1s2. Every single element after helium has a 1s2 to start off their electron configuration. Can you give me an emoji in the chat if you follow that? Okay. So all right. Now, if we are to go to something like, so what that means is if I say, oh, what's the electron configuration of PO, polonium? Or what's it start with? It would start with 1s2. Because what you're describing there is that you have a 1s subshell, a super small sphere with 2 electrons in it. Now, after that, we go on to row 2, which is right here. No worries, Katrina. If I asked for, so this is going to be my, I'm going to scribble this out. My first electron configuration for helium is 1s2, done. Now I'm going to go on to nitrogen. What's the electron configuration for nitrogen? Well, it starts just like every single other element after helium, and so it starts with 1s2. Then it's helpful to look, well, which number of, which group is nitrogen in on the periodic table? Or which row? It's in row 2. Now, when we're doing this, what I think is helpful is just to try to kind of go across and then come back and come here and go this way right here. Just sort of counting up the atomic numbers. Therefore, you're counting up the number of electrons. Now, this second spot right here, or this second row right here, we have to account for those electrons because we're building up nitrogen. This is known as the S block because all of these electrons, or all of these atoms, have electrons in a S orbital or S subshell named after or numbered after the row in which they are on the periodic table. Now, when it comes to nitrogen, we go 1s2, 2s2. So when we add these exponents, that's 4. So we've accounted for 4 electrons of the total that nitrogen has, which is 7. Now, I'm going to kind of jump across the center of this periodic table. This is row 2, but this is within what's known as the P block. So I'm going to say 2p3. When it comes to electron configurations, if you add your exponents, that's going to be the number of electrons that that element has as a neutral atom. So if I go on from 2p3, well, let's say that I went on to, let's look at chlorine. Actually, we did chlorine last time. Let's go with argon. Argon, Ar. I'll give you a second to work on this and then I'll jump in. Okay, so argon is going to start with 1s2. We can kind of duplicate what nitrogen has so far. So we're going to go 1s2, 2s2. I always like to kind of check things off as I'm moving through and moving up to the element that I'm talking about. So 1s2, done. 2s2, done. Now, 2, and this is one thing that's a little bit different, p. This p block right here, well, a p subshell can hold a total of 6 electrons. So 1, 2, 3, 4, 5, 6. So 6. And if you're thinking, okay, well, what's a rule that I can follow? I'm going to jump back. S subshell, 2 electrons. P subshell, 6 electrons. D subshell is going to hold 10 electrons. And would anyone using this kind of pattern, I'll give you a second to look at the pattern, and then whenever you're ready, tell me how many electrons an F subshell can hold. London, awesome. 14. Okay. Now these are numbers that I want you to know, and I'll ask you, I'll ask explicit questions on the exam, like how many can this subshell hold? What's the maximum number of electrons that this subshell can hold? Okay, so now I'm going to go back. So 2p6. Now I'm going back over here. This is 3s2, 1, 2, and then last but not least, 1, 2, 3, 4, 5. Argon has an additional 6, so that is 3p6. Okay, so questions that I want you to be able to answer. I want you to be able to answer how many electrons can a subshell hold? A specific subshell. If I say the P subshell, how many electrons? I want you to say 6. If I ask about the F subshell, I want you to say 14. Next up is if I give you an electron configuration, I want you to be able to know that if you add up the exponents, you will get the total number of electrons that that neutral element has. So argon, for instance, as a neutral element has 18 electrons. Let's add our exponents. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18. So if you add your exponents up, you're going to get that specific element in the neutral form. Okay, now I'm going to go on from here because this is just intended to be a little bit of a review. I've given you 3 elements, electron configurations. If you want more, I mean, they're all displayed on here. One thing that I want you to notice is that if you look at argon, and look very closely at it, one of the things that you'll notice is that it is Ne in parentheses. And then after that, you'll see 3s2, 2p6. And you might think, well, what's with that? Well, what that is doing is it's kind of using a shorthand notation. This row or this column, this last column, is known as your noble gases. So this shorthand notation is using the nearest preceding noble gas and then adding everything that's after that. So for argon, the nearest preceding or the nearest previous noble gas is neon. So we put neon in a bracket and then we say 3s2 or sorry, 3s2 3p6. Sorry about that, not 2p6. So that's just the shorthand notation that's used throughout the periodic table. Now, we are not going to go beyond argon. I'm stopping there. I do want you, however, to know about the number of electrons that the F and D subshells can hold, and I want you to be able to pinpoint an element where it is on the D or F block. So if I say this element is located within, and I gave you the element PD for palladium, which you will have a periodic table on your exam, I want you to say, oh, well, that's in the D block. So that has electrons in a D subshell. Okay. Now, the next thing that we want to cover here is your valence electrons. It's possible that if you've taken a chemistry class or maybe even took IPC, that was the class I took as a freshman in high school, integrated physics and chemistry, you've maybe learned about valence electrons. Valence electrons are considered to be your outermost electrons. And there's a quick way to determine the number of valence electrons that your what are called main group elements have. Now, for your main group elements, what we do is we kind of omit or skip over this central region. Now, if you're curious as to why, well, one reason is that these main group elements, those that are here and here, are kind of your most abundant. That's not to say those are the only ones that you see if you go to the beach and you pick up sand or anything like that. But these are the ones that chemists in other fields like organic chemistry and biochemistry, physical chemistry, they're going to most often deal with those main group elements. Now, these main group columns are known as 1, 2, 13, 14, 15, 16, 17, 18. Now that's counting very similar to how my kindergartner counts from time to time, where he'll say 1, 2, skip a few, 99, 100, and he's counted to 100. I taught him that one. The 3 through 12, this central region, these are known as transition metals. And transition metals are important, but for the application of number of valence electrons, your transition metals can have a large number of different valence electrons. For example, iron, Fe. Iron is a pretty important element. If you don't get enough of it in your diet, does anyone know the affliction that you can develop if you don't have enough iron in your diet? Anemia. Absolutely. And sometimes if somebody has anemia, they'll appear really tired, and that's largely because they're not getting enough oxygen throughout their body. And classically, if you am I record? Okay, good. I am recording. Sorry, I have these moments during class where I'm like, oh no. But here we are. We're recording. Usually if you have anemia, sometimes it might be addressed with eating a steak or something like that. Something that gets you lots of, heme and hemoglobin back into your system. Now, iron, I bring that up just because iron can have a couple of different numbers of valence electrons. Iron can be, it's a metal that can have 3 valence electrons. I don't know why I wrote over their other letters, but it can have 3, 7, 4, 2, a large number of valence electrons. And so it kind of jumps around and goes a little bit crazy there. Now, with that said, we focus in for our valence number calculations. Don't worry about it. Somebody, private message, somebody said they woke up late. Happens. Um, when it comes to our valence electrons, I want you guys to know the valence number or the number of valence electrons that your main group elements have. So on an exam or a quiz, you will see a question like this. Sulfur has how many valence electrons? And for that, I'd want you to just come up with 6. You might think, well, where does 6 come from? Well, Six comes from a couple of different places. If you want the quick answer to that question, where does the six come from? Well, you just scribble out the one. It's in group 16. If you're like, yeah, that's the shorthand, quick way to do it, but where does the six come from? Well, if we think about the electron configuration of sulfur, and here I'll go ahead and use that core notation or that shorthand notation. Sulfur has an electron configuration of neon, our nearest preceding noble gas, the nearest noble gas upstream of it. And then 3s2, 3p4. Add those exponents for me. 2 plus 4. Dang it, Joel. It's confusing when I make a mistake like that. I apologize, everyone. 3 plus 4, 6. 6 is our number of outermost electrons. So what that means is that the S and P subshells, the number of electrons that those hold, tell you the number of valence electrons that something has. So I'll give you a question like that. Alternatively, I could give you a question like this. An element with an electron configuration of, I'm going to bracket, and then I'm going to say XX, so just a filler, or actually with a valence electron configuration of 3s1. How many valence electrons does that have? Just one. What about if we say 3s2, 3p5? 7. Okay. Now, if you can add that up, you're in great shape. Now, one of the things that I want you to know and I want you to remember for the future of this class is, and I'll ask a little bit of help from you guys, what did I call this row right here, this column? 8, but what did I call those elements? Noble gases. That's absolutely right. So those are our noble gases. Now, if I were to say noble, if I were to describe somebody as noble, if I were to say like Dr. Damphus is a very noble person, give me another word that would come to mind for you. Ooh, regal. I like it. Prestigious, upstanding, all of these things. That's somebody I would like revere and kind of respect, and I'd be like, good, good and smart. Now, all of those are great words. Give me a one if you would agree that somebody who I would describe as noble, I would probably also describe as like stable, like they're even keeled. Okay. That's what I want you to think about with our noble gases. They're very stable. They're not going to be reactionary, and they have kind of reached it's almost like they've reached a level of satisfaction with their life. Like they're retired or something like that. And they're like, when I look back, I think I did pretty good. Okay, I'm happy. So I want you to think about your noble gases as stable. Now, in this case, whenever I say stable, I want you to think about them as electronically stable. And what I mean by that is they have the number of electrons, specifically valence electrons, where they're like, I'm good. I don't need to gain any. I don't need to lose any. I have the right number of valence electrons. Can you give me a 0 if you follow that? Okay, so our noble gases, they have the happy number of valence electrons. Now, this is significant, this is important because that gives us an idea for what different elements want to do. Do they want to gain electrons or do they want to lose electrons? If we take fluorine, for instance, fluorine here, how many valence electrons does it have? Add it to the chat. 7. We know that 8 is the number that elements want to have to kind of be happy. So if fluorine gained an additional electron, would it have the same electron configuration and be kind of as stable and happy as neon? Add a Y or an N to the chat. If it gained one more, then it would have 8. And that's where we're going. That's what we want it to do. Sorry, I asked a question that I was supposed to be like a teaching thing, but that's where we're going with respect to fluorine. Fluorine, chlorine, bromine, iodine. Yeah, if all of these with their 7 valence electrons, if all of these with their 7 valence electrons picked up one additional electron, then they're going to be like, oh, this is a relief. I've got the same number of valence electrons as a noble gas, and I'm happy with that. That's what I want. So, can you give me a 5 in the chat if you follow that something like fluorine wants to gain one electron? Wonderful. Now, fluorine with 7 valence electrons gains one, and then it's as happy as a noble gas. Can you tell me in the chat how many electrons something like oxygen would want to gain in order to attain that same happiness? Perfect. 2. Okay. I got a private message question. Would it be considered a different atom then if it had another electron? That is a fantastic question. No, it would not. Because remember, the number of protons, when we change the number of protons, then we change the element. When we change the number of electrons, we're not changing anything. Because electrons have no mass, it's almost like they got some sort of static electricity or something like that. It's a great question. Okay. So, yeah, if oxygen picked up 2, oxygen's going to be like, great, I'm just like a noble gas now. Okay. So, our takeaway from this slide right here on this slide deck is what is our, actually, let me go ahead and write these out. Actually, yeah, I'm going to clear some space. So, what is the maximum? That is a great question. So, the maximum number of electrons that something like fluorine can hold would be, okay. Most direct answer to your question there, Nick, is 1. Now, the next layer to that question would be kind of a, oh, actually, here we go. If it held, so the maximum number of electrons would be 10. 10 is because that's including all of the electrons. Um, additional, how many additional electrons will a neutral fluorine take on? That's 1. Now, if it took on more than that, well, then it's probably going to become unstable. So that's where this is all kind of a balance. Now, I'm going to add kind of our takeaway notes from this slide right here. So we want to know number of valence electrons based on p table positioning. We want to know electron config of noble gases. And then we want to also know everything wants noble gas config. Okay, so I'm going to space these out a little bit. You know how if you were looking for like what are learning objectives from this slide, it'd be these right here. These are the kind of important takeaways from this slide right here. Um, okay. Can I get a One in the chat if you say, okay, cool, I'm good with that. I know how to practice that. And a two if you're like, is there anything else? I'm sure you'll get to it, but would hydrogen and row 2 need even more valence electrons to be stable? Okay, that is a fantastic question. Okay, so if we talk about, let me see, just a second. I got to pause my slide deck so that I can scroll through some of these guys. Okay, so I got you guys paused, and then, all right. Now, okay, I'm pause. So I got a private message question, which is a great question that reads, I'm sure you'll get to this, but would hydrogen and row 2 need even more valence electrons to be stable? It's a fantastic question. Okay, I want to use two examples to address this. Now I'm going to clear all my notes on this slide, erase all, and okay, there we go. So I want to use two examples for this. Let's say that we had, let's talk about lithium. Again, great Nirvana song. And then let's talk about magnesium. Not a Nirvana song. Now, these two these two atoms, they have one valence electron and two valence electrons, respectively. They have, okay, so if we take lithium and think about, let's say, the noble gases that are kind of flanking it. On one side, lithium has helium. Helium has an electron configuration of 1s2. Lithium has an electron configuration of 1s2, 2s1. On the other side of lithium, there is neon. That has an electron configuration of 1s2, 2s2, 2p6. Give me a W if you follow and agree with all that information that I put up there related to lithium. Okay. Now, let's imagine that you are lithium. Lithium has two different options. Lithium can lose one electron. So we're focused in on, can I go a little bit slower? Absolutely. We're focused in on lithium. And we want to know, what is lithium going to do to become its most stable form? That's the question. Li, stability. That's what we're seeking to answer. Lithium's two most stable elements near it are helium and neon, because those are both noble gases. If we look at our noble gas electron configuration, for helium, it's 1s2, and for neon, it's 1s2, 2s2, 2p6. And we basically confront lithium and say, listen, you can either become stable by adopting or taking on the same electron configuration as helium, or you can become stable by taking on the electron configuration of neon. Can you give me an X in the chat if you follow that kind of proposal? Okay. Now, let's imagine lithium going to take on the electron configuration of helium. Now, a fair question there is, well, what do I mean by taking that on? Taking on the electron configuration? So, like, taking its three electrons and plugging it into there? No. The way that lithium would take on the same electron configuration as helium is by losing one electron. Can you give me a T in the chat if you follow that and you agree with that idea? Okay. So I'm going to call that kind of proposal A. A is that lithium will lose one electron and then it will become stable by having the same electron configuration as helium. Now, when that happens, I'm going to go over here and I'm going to say, okay, well, lithium, tell me how many protons does one atom of lithium have? And we know three. We know it's three because right here, our atomic number is three. Okay, so three positive charges, and it loses one electron. Can you tell me the charge that lithium will have if it only has one, or sorry, it has two electrons and three protons? Plus positive one. Absolutely. Okay, so that's option A. Now, option B. Okay, let's go back to our base or our neutral lithium. Okay, so in order to get to lithium, or sorry, the same electron configuration as neon, tell me in the chat, anyone who's ready to, tell me what lithium would have to do. Add seven electrons. Okay, I agree with that. So it'd have to gain seven electrons. All right, so tell me what the charge for lithium would be if it has three pluses, and that would be a total of 10 negatives. So option B. Does everyone agree that it's exactly, great job, Kelly, -7? Okay. Now, you're right. Those are our two scenarios. I have some thoughts with respect to this. My first thought is, what do you think is easier? If you think about, or I want you to think about losing or gaining an electron as being kind of equally challenging. So to lose one, it's the same challenge as to gain one. Kelly, you're right. It's more likely, lithium is more likely to lose one electron and take on that electron configuration equal to helium than it is to gain seven. So this is getting into something that we will talk about, and this topic is known as ions. So some things with, or an atom with different numbers of electrons. Now, with that in mind, I'm going to go ahead and put a big X over this because that's not going to take place. That's extremely unfavorable. Now, the second thing that I want you to think about, I always like to, kind of simulate things in my mind, like what does this actually look like? Let's think about, and I'm going to draw in the lower left-hand corner. I'm going to draw the protons that make up a lithium nucleus. One, two, three. Can everyone see? Is there a visual representation of lithium adding or gaining electrons? Well, you know what? I can go ahead and give you a drawing of one. Let me see just a second. Okay, there we go. So we've got lithium. Actually, let me go ahead and I'm going to draw the nucleus, and I'm only going to draw the protons in the nucleus just so I can keep it a little bit more simple. Our 1s orbital has two electrons on it. Our 2s orbital has one electron on it. Okay. Now, the way that lithium is likely to go, or will go, is this right here. Plus, plus, plus. Then here's a first sphere, the 1s orbital. It's got two electrons on it. Li minus 7 looks a little bit like this. Same number of protons within the nucleus. Electron, electron, so that's minus. Those are minuses. And then 2s. And then that next level is and I'm just going to draw a circle to represent this rather than those dumbbell shapes. 1, 2, 3, 4, 5, 6. Okay, so we have kind of concluded that this is the one that's likely to take place. Now, to kind of affirm that and kind of like hammer that or like put that in your head and help it work a little bit better, the way that I've always thought about it is, and again, I have kids, and so I use lots of kind of folksy, hey, this is like my kids sort of examples, and I apologize if you're like, this is lame. But that's what I know. That's my world. Um, when my wife and I go to, we'll say Target, whenever we had two kids, it was something that was a little bit easier to manage because my two kids, okay, there's one parent or there's two parents, two kids, done. I can kind of keep an eye on them. Now I have four kids. When my wife and I go to Target, it's like, okay, well, you're watching this one, you're watching this one. Okay, but what about the other two? Oh man, they're somewhere in the store. That's our objective. We know they go to the toy section, but our objective is like, let's keep them contained. So it's easier for these protons representing the parents, and these two kids, or these two electrons representing the kids. So if you think about this model right here, 3 positive charges keeping 10 negative charges in place, that's going to be a mess. So that's just unfavorable. And so that's why that's one of the reasons that's not going to happen. Now, with that said, our first row on the periodic table has lithium, sodium, and potassium. These are what are known as alkali metals. And these metals react very violently. This should work in this slide. Oh, dang it. Okay. I know how to do this one. Okay. They react very violently within water. And let me pull this up. So whenever I say they react violently, they will basically, if you put those metals into water, they will catch fire. So here we've dropped lithium, sodium into water, and in just a second, so that is how they react very violently. And that violent reaction is basically just them losing electrons. So lithium, for example, will lose an electron and it will catch fire. Okay. So now what we're looking at, and where we're going to go from here, is we are going to be tackling a couple of other things in the periodic table. So those metals react violently, whereas nonmetals, what they're going to exist as is they can exist as a gas, like chlorine, or sulfur can exist as a soft, brittle solid. And that's going to be our kind of foray into the periodic table. So we have a couple of scientific laws that we need to go over. These scientific laws include, well, mass. So if you look at these two substances, what do we have here? We have a total mass of 173.64 grams. So these two solutions in these two beakers, or in our grad cylinder and in our Erlenmeyer flask, when they are mixed together, they will change color. There will be a change observed, so there will be a reaction, but the mass does not change. So this is kind of going on the idea that matter cannot be created nor destroyed. So this is known as the law of conservation of mass. Matter is neither created nor destroyed during a chemical reaction. So when we look at these two solutions, just imagine that this is I think that this is iron chloride, and this is sodium hydroxide. So when these two substances are mixed together, what you get is iron oxide. Now, the important part about this is not necessarily the reaction that takes place and the product that's formed, but instead, what's important here is to look at the that a chemical reaction has taken place, but no mass is actually lost here. So here what we have is the law of conservation of mass, where we have that same sort of thing. Now, I have a private message that is there a scenario where you add two different masses and it loses mass? That's a great question, and it's possible, but chances are what you're losing is simply going to be water mass. So, if you were to, like this morning, I made eggs. And whenever I made eggs this morning, well, some water, as I put them on the balance, what I noticed was that, well, the mass was going down. Why was the mass going down? Well, the mass was going down simply because of the fact that there was water within that was evaporating. So the steam was raising off, but that's not that water that was in the eggs that's evaporating. Well, it's just going from a liquid to a gas. It's not totally disappearing. Instead, it's just kind of transitioning states. So here what we have is a solid known as mercuric oxide. Now, whenever that is heated, you get 100 grams of this. What you get is 92.6 grams of mercury and 7.39 grams of oxygen. Well, if you were to add those two together, 92.61 plus 7.39, those would equal 100. Now, if I did the same thing, and rather than 100 grams of this, I used 200 grams of this, well, the result would be 2 times as much mercury is produced and 2 times as much oxygen is produced. And so I have basically an even ratio that's going to be produced there. Now, one example that you've probably seen before is I think the first time I saw this was maybe like 5th grade science fair volcano, where you added vinegar and baking soda. And when you added vinegar and baking soda to one another, what's going to happen is a gas is going to be evolved. Okay, I got a message of, does fusion result in a loss of mass and therefore a gain of energy? My understanding of fusion is elements that are fused together. I'm not a nuclear chemist. So it is the fusion that will, I believe, produce energy, which is why the idea of a fusion reaction is powerful when it comes to energy production. Okay, so vinegar and baking soda. You produce a gas here. That gas evolves. That gas is carbon dioxide. Now, there are laws of chemical combination where you have the conservation of mass, definite proportions, and multiple proportions. Here we have CO2 or carbon monoxide and O2 that will produce carbon dioxide. So our law of conservation of mass is that these reactants, CO and O2, react in a perfect ratio to one another to produce CO2. The law of definite proportions says that, well, carbon dioxide will be produced and carbon and oxygen will form in this particular ratio. If you ever get carbon dioxide is always CO2. It's nothing else. It's always CO2. Whether you have 1 gram of it, 1 molecule of it, a million grams of it, a million molecules of it. You have the law of multiple proportions, which says carbon monoxide and CO2 are two different ways in which carbon and oxygen can kind of mix together to produce different compounds. So all of these kind of rules are assembled in something known as, oh, so if it were CO3, would it be, so CO3, what would it be? Carbon trioxide. So that I'm happy that that's brought up because CO3 would be different from CO and CO2. It's carbon and oxygen kind of assembling to make something different. So Dalton's atomic theory says that all matter is composed of extremely small and indestructible theory or particles called atoms. So everything can be broken down to an atom. And that was Dalton's atomic theory long, long ago. Now, is this something that we know to, you know, is there anything smaller than an atom? Have we talked about things that are smaller than atoms? Yeah, subatomic particles. So, can things be broken down farther than an atom? Yeah, we know that they can be. Now, another proposal from Dalton's atomic theory is that elements are made of just one type of atom that is unique to that element. Okay? So, Dalton assumed that all atoms of a given element were identical in all respects, including at mass. But we know that's kind of flawed because we know about isotopes. So we've got subatomic particles. Compounds are formed when atoms of different elements combine in fixed proportions. And so this is the law of definite proportions. So you can have CO, CO2, CO3. Then a chemical reaction involves a rearrangement of atoms, but there is no breaking, destroying, or creating atoms. Okay, so any chemical reaction, you're going to be conserving mass. So from reactants to your products, you're going to conserve mass. It's not going to be created or destroyed in that reaction. Can you give me a one in the chat if you follow these modern modifications?
My chat has been disabled.
Oh, it has? I thought that. Okay, so everyone. Okay, sorry. Try again. Okay, great. All right. So these are Dalton's atomic theories that have been updated to present day. Now, that's all important information because when we go on to kind of elaborate on compounds and how they're assembled and everything like that, that's an important component here. So we've got the periodic table, and we've talked about a couple of different things. Which one of these represents an element, A, B, or C? Well, for these different depictions, you'd look at this and say, okay, well, that's different atoms. This is different atoms. This is a different atom. So A and C here are different kind of representations for atoms and how different atoms and molecules can come together. B, however, would be something like H2. So two atoms of hydrogen that come together. So there are a series of elements that are known as diatomic gases. H2, Br2, O2, N2, Cl2, I2, and F2. When I was in high school, my teacher taught us these, and she said that they are H. Roncliffe. It's a nice little name for someone that we could call and say, like, aha, there's H. Roncliffe. Those are our diatomic gases. That's our mnemonic that we can use. Now, when we go over here, our element symbols. We've talked about these, our atomic number. This is sometimes denoted as Z. Z indicates the number of protons that an element has. Fe is our chemical symbol, and that mass right there is our weighted average. Now, this accounts for our atomic abundance. Or the relative abundance of different isotopes. Okay, so we've talked about the periodic table a little bit, and these elements are organized and arranged based on their atomic numbers. Our atomic numbers are increasing. They go from 1 all the way up to 118. Now, if you look at the different colors of these, they all denote different things with respect to um, physical and chemical properties. These over here are your, or actually, let me rephrase it. Let me change that. Mhm. Generally, whenever it comes to the periodic table, the left-hand side is considered to be your metals, and the right-hand side are your nonmetals. Your metals and your nonmetals, they are going to have different properties. Just as I showed you a little bit ago, the video of the metals that were highly reactive in a solution of water, your nonmetals sometimes are going to exist as a solid at room temperature, or they're going to exist as a gas. Metals are going to have extremely high boiling points and melting points, whereas nonmetals are going to have lower melting points and boiling points. Now, if we go to look at atoms versus molecules, a molecule is a group of atoms chemically bonded to one another. The standard colors that are used to denote these different atoms, blue for nitrogen, red for oxygen, black for carbon, and white for hydrogen. So on the left-hand side here, what element or what molecule is that? Water, H2O. On the right-hand side, CO2. Perfect. Carbon dioxide. Awesome. Now, if you were to look at something like this, caffeine, just so we're all on the same page, I'm not expecting you to have this structure memorized or anything like that or know this. But what I want you to be able to do is if I showed you a molecule like this, I want you to be able to kind of dissect it and come up with the formula. This right here is known as a molecular, or sorry, this is known as a structural formula. A structural formula shows all of the atoms within a molecule and their positioning and which ones are bonded to which. So, in order to come up with a formula for this, a molecular formula, here's what we want to do. We want to take on carbon. And I always like to start with carbon, and I'm going to say C. And then I'm going to count up the carbons. And I always like to go ahead and just keep a tally. So I'll say 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to say C, and then I'm going to put a subscript 8. The next thing that I'm going to do is I'm going to look at my nitrogens. Nitrogen are the blue ones. 1, 2, 3, 4. C8N, what did I say? 4. Last but not, well, not last but not least, I'm going to go on to oxygens. 1, so 1 and 2. O2. So I've got carbons, nitrogens, oxygens. Last but not least are hydrogens. Hydrogens are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. H10. Okay, so C8N4O2H10. That is what this formula shows me. Now, the would we be incorrect if we counted the elements in a different order? That's a great question. So I think that this question is like if I said C8, H10, N4, O2, is that what you're asking? Yes. No, both of those would be acceptable. There is pretty much a standard. Okay, would your answer be wrong if you started with it? Okay. Um, there are some general rules, and typically the first element that's listed is the one that's farthest left on the periodic table. Now, as you can see there, you're like, but wait a minute. I know the periodic table. Hydrogen's farthest to the left on the periodic table. And you'd be right. Hydrogen is kind of the unique exception. Hydrogen has all these rules that it just kind of doesn't follow all of them. So typically we start with carbon and then H10N4O2. Between these two, or let me just say that the answer options you're going to have on your exams, I'm not going to give you, well, these two as both viable answer options. So that's something that you can kind of account for on your exams. Now, with that in mind, this right here, it's kind of simple because what we've got is, well, it's H2O, H2O, H2O. We've got 3 water molecules. How are we going to display those 3 water molecules? And how would we write this? Well, my first question for you guys, and answer Y or N, Are these all bound to one another? Are these three water molecules bound to one another? No, they're not. So, do they make up one molecule? They don't make up one molecule. So, we would not write H6O3. So, I'm going to circle this and put a big X on that because that's wrong. So, how do we write that? How do we communicate that there's three H2Os? Three H2O. Okay, that's what we do. Now, with that in mind, I want to really stress that this is not equal to H6O3. Those two are not the same. 3H2O is not the same as H6O3 because of the fact that, well, this whole thing right here suggests that all of these atoms are bound to one another. Whereas this right here says that you have three of this one type of molecule. I'm going to erase that, and now we're going to look at these different numbers. This 3 is known as a coefficient, whereas that 2 is known as a subscript. Now, when you're writing out a formula, those are the two numbers that you're going to use. There are some times when you will see a superscript, but that superscript is going to be a positive or negative. A subscript would be a number. So your coefficient, 3, and then your subscript, 2. Now, with that in mind, if instead of 3H2O, let me ask you this. Let's say that I had H2O and I said, oh, well, how about H4O? Is H4O water? Y or N to the chat? No, it's not. So what if I wanted to communicate that I've got two water molecules, H4O2 versus 2H2O. We got A versus B. A is going to be correct there. So your rule that I want you to follow is you cannot change your coefficients, or sorry, you cannot change your subscripts, but you can change your coefficients. All right. Now, does anyone have any questions about what we've gone over so far today? Okay, so what I wanted to talk about for let me go ahead and we've got a couple more minutes, so I'm going to tackle this day 5 stuff. So day 5 is all about ions. We've talked about ions, or we just kind of talked about ions because an ion is an element that gains or loses an electron. So, for example, Li plus is an ion. F minus is an ion. Now, the significance of this is these either gained or lost electrons. Now, what I want you guys to take away from this is if something I want you to think about that for a moment. If something gained electrons, I'm going to change this something to if an atom gained 2 electrons. What do you think the charge is going to be, positive or negative? Kelly, perfect. -2. It's going to be a negative charge. If something, if an atom lost electrons, lost 3 electrons, what's its charge going to be? +3. Now, for this, what I would recommend that you do is, and I always go back to lithium. I always think about lithium as my kind of my base molecule or my base atom. I always think about lithium and say, okay, Li has one. Lithium as a neutral atom has plus, plus, plus. Electron, electron, electron. Okay, so there is lithium. It'll give me a Y or N to the chat if you agree and follow that is lithium as a neutral atom. Okay. Now, I use this because it's simple and it's quick to draw. If I'm going with the idea of, okay, well, it's gaining electrons, I'm going to use lithium as my model. I'm going to say, okay, I'm going to draw one additional electron. What is the charge of this right here? -1. What is the charge of this right here? Perfect. Understanding that is at the heart of everything that you need to know for charges of ions and understand what an ion is. An ion is something that results from gaining or losing electrons. Today, just because we're doing the authentication, I got a question about head on out. Everyone's getting credit for attendance today. Just because I'm still making sure that everyone can join the class. For the homework, instead of embedding the images, can I just upload a picture of my own paper? As long as it's one complete document. Okay, I'm going to go ahead and stop right here, and I'm going to open the floor. If anyone has any questions, you're more than welcome to ask. Other than that, though, I hope that you guys have a great Thursday. I've got office hours starting at 11. If you've got any questions, feel free to drop by, and I will see you guys on Tuesday. Thank you guys very much for coming to class and your participation and everything. It was awesome. Chat, where did chat go? Okay, can it be two? So it can't be two PDF files. If you have, I'd prefer that it's just one, so then you only have to upload one document. Um, which I think you can do that with Acrobat and kind of throw them together. Um, if you have issues with that, let me know. If you can't do it, then yeah, two will work. Just notify me. For the homework, is it okay if I use my iPad to write on? Yes, you absolutely can. I just want your own penmanship. Okay, I submitted it twice with 2 PDFs and then the other one in the Word doc. So one PDF. Okay. Which topics will be present in quiz 2? Quiz 2, thank you. Quiz 2, which opens, I believe, at 11 a.m. today, is all about electron configuration. I turned in my homework last night because I did not know the deadline changed. I got one valence. Absolutely. The most recent homework is the one that I will be grading. Okay, thank you. I have an app called Chem Scanner that turns a picture into PDF and allows me to upload it to the assignment. Am I able to submit my assignment that way? I believe so. Yeah, that should be no issue. Tuesday, you said you had some additional study resources. Yes, I will make those available. Let me put that on my list. And then we have homework this week as well, correct? I'm not going to release another homework assignment until this first one's been all completed. So your next homework assignment will go up on Tuesday. I turned in my homework yesterday. I printed out the assignment, wrote on the 2 sheets. Is that okay? That's fine with me. That works.